Hello everyone and welcome to the second lesson in the Introduction to TypeScript course. I'm Giuseppe Maggiore and I will be our speaker today. Alright, now what we saw in the last lesson was an introduction, just in general, why would it be nice to know TypeScript, what are the possible applications, a little bit of the history, and especially we set up our TypeScript and JavaScript pipeline. Just as a quick reminder, we have a TypeScript file, and by running the command yarn tsc -w, the TypeScript compiler is going to run every time one of our .ts files, one of our TypeScript files, gets modified and saved on the hard drive, and then we command node bin/main.js. In our case, we run our program via the node.js interpreter. The pipeline is set up in such a way that in the bin folder we will get the compiled JavaScript files which can be executed. Okay, so today we're going to discuss variables, basic types, primitive types and expressions, and then we will see some of the most, let's say, traditional constructs of modern programming languages such as conditionals, loops, etc. After this class you will have an intuition of, well, an intuition, hopefully better than an intuition. You will understand how the language works at the most basic level of processing information. Good. So, the most basic construct of, you could say, virtually any programming language is the so-called binding of values to names. So we have names, like variable names, parameters, whatever, and those names give context to some information. So if someone simply said, okay, 38, yeah, 38 on its own without any sort of name is just data. But when I say that the age is 38, by binding the value 38 to the name age, all of a sudden I'm providing a sort of context, you could say. And the binding of a name to a value turns data into information in an intuitive sense. Okay, there are three fundamental ways of binding names to values in JavaScript. Let, which creates a variable, var, which is the old style of creating a variable. Now let's use underscores, and const, which creates a constant. Now, we are going to ignore var because it's a legacy construct that doesn't really behave very well, especially when it comes to scoping. So we're going to focus on let, because let introduces variables that scope properly. So with let, we do not just bind something, a variable like age to value 38 or a variable like first name to Giuseppe, but because the name is a variable, we can rebind the value. So one could say age is age plus 1. This happens to everyone about once a year, and the language doesn't complain. On the other hand, the surname, being declared as a constant, is bound to the value once and only once, and this binding cannot be changed. So if I were to say surname is something else, yeah, you can see that already I'm getting the red worm of annoyance that says you cannot assign to surname. The error is pretty clear, is pretty self-explanatory. It says you cannot assign to surname because it is a constant. The same error can be seen here in the console. As soon as I save, I get to see the error, cannot assign to surname because it is a constant. And in case you're unfamiliar with this way of signaling errors, this is stating, okay, in file main.ts at line 6, okay, starting at column 1, the column is usually a bit less than useful, the error takes place, and then we get the line where the error is happening. Then we also get found one error, just one error. In some cases you might have more than one, and then the system is back to watching for file changes. Okay, so surname is a constant, we cannot reassign it. So let's remove this offending line of code. With double slash, I add a comment. You can see that the line of code has changed color. The error has disappeared because comments are just any sort of text that the compiler is ignoring that we leave for reference or for explanation or whatever. Okay, now it is possible to print things with console.log, so I can make my program attempt to do something almost interesting by simply printing our values. There you go, Giuseppe Maggiore 39, because the value has been changed. So when I mentioned scope before, scope is any block in our program that is enclosed between curly brackets, with one scope that is not enclosed in curly brackets being the main scope of the program. Within a scope, I can define or redefine variables that exist until the corresponding curly brackets. So this means that I could define first name again, or actually no, let me show something else. No, I can define surname again, and now I do not get any complaints from the program. So let's say that the surname here is Smith, and you can see that there is no problem. If I were to move the rebinding of surname to Smith outside of the curly brackets of the scope that I just defined, of course now I get an error because, well, it says you cannot redeclare block scoped. Yeah, okay, it shouldn't say variable, it should say constant surname. And it is correct because once you bind a name in a scope, yeah, that's it, that name is bound and it's bound forever. The same applies to let. But if you declare a new scope, well, within this scope now the surname is Smith. Let's repeat our printing. Now you can see that if I run the program, I get Giuseppe Maggiore 39, but also Giuseppe Smith 39, because within the scope defined by the curly brackets, the surname constant is bound on line 13. We might also make another little experiment here, and what we are going to get is Giuseppe Smith 39, because in here the surname again is the last definition of the surname. At this curly bracket, the constant surname is deleted because the scope is cleaned up, and when I print surname again, then line 16 will print the surname defined on line 3. The IDE, Visual Studio Code, actually gives us an interesting insight in this, because if I click, control click or command click depending on your operating system on the variable, you can see that the cursor jumps to line 3 to show this is the variable, this is the binding that defines surname. But if I do it here on line 11, look what happens to the cursor, it jumps to line 9. We will look at scopes. We will look at scopes extensively. Scopes are very important when defining things like classes, when defining functions, when defining all sorts of constructs that manipulate the flow of the logic of our program. And yeah, let respects scopes very well, so that's the reason why we're going to use let, and we're never going to use variables. Okay, I hope you don't mind me trying to explain every word I say, but if I mention a word like scope, because programming is an engineering discipline derived from mathematics, everything I say can be and will be explained. I will try to avoid appeals to intuition because I frankly find them not required. When things can be explained, I'd rather explain them and give you the tools to follow completely. Alright, now TypeScript supports the usual primitive types with a series of related expressions. What are primitive types? Primitive types are containers of data with a given structure supporting a series of operations. Let me begin by showing numbers. Let's declare two variables I and j with values 2 and 3. Both values I and j have, both variables, I and j have type number. We can see types by just hovering with the mouse on the variable, and then we see after the colon the TypeScript tells us, hey, I is a number, that we will really dive into types later. Variables of number type support all the usual arithmetic expressions. We can add, subtract, multiply, divide. We can perform the modulus, so the remainder of the division. We can calculate the power, so in this case 2 to the power of 3, and we can do all sorts of mathematical things by using the math.library, math.whatever library. So here we have sine, cosine, logarithm, whatever. If we run this program, by virtue of this program not giving any compiler errors, we can be pretty sure that the program is going to behave reasonably without blowing up. You know, notice that all values that we are dealing with of type number in TypeScript, just like in JavaScript, are are relative numbers. So they all have, so they are all numbers with a comma. The comma, the part with the comma, the fractional part, is hidden from printing, but it's always there lurking. And when you divide integers, it's quite likely that you will get that you will get digits after the comma, like we see in the fourth printout, 0.66666. Doubles are quite precise, but if you don't want to have values that can contain some slight imprecision, it is possible to extract the closest, extract the floor. So in this case 0.6 will become 0. The ceiling, in this case 0.6 will become 1, so we approximate to lower or higher, to the lowest integer that's closest, or to the high okay, the floor is the floor truncates the part after the comma, and the ceiling fills up until you reach the next integer. Or we could even just ask for the closest value, and this would be the rounding. And in this case 0.6 gets rounded to 1. Okay. In TypeScript, it is also possible to use big integers by adding the n suffix to our values. Now you can see that the type has changed from number to big int. Big ints are just integers. They don't have a fractional part. They support the same operations as numbers, plus, minus, etc. But you might notice that round, which expects a number, does not work anymore. And the same applies to the logarithm. In this case, we would have to cast back. Now let's run our program. You can see also that in printing we get a hint that the values that we just printed are naturals. Are the n, I suspect, strongly stands for natural number, or just, no, I don't know what it stands for. Yeah, doesn't matter. But in any case, this means that these values do not support digits after the comma. Numbers and big ints represents values that are, for all practical purposes, can become so large or so small that we can almost think that they are infinitely precise. Well, they aren't. At some point we will encounter the limit of the representation, which is many billions of values, but still there is a limit. On the other side of the spectrum, there is a sort of numeric value that only supports two values, 0 and 1, or I should better say true and false. These values are booleans, and they are represented as literally the strings of text true and false. Well, because true and false are essentially 0 and 1, there are some algebraic operators which are AND, OR, and NOT. Now, AND will give us true when both operands are true. So if you say, is the car red and with leather seats, This will only be true if the card is both red and it has leather seats. If the card is blue but it has leather seats, well, the statement will be false. If the card is red but it doesn't have leather seats, then the statement will also be false. Or, on the other hand, is true if at least one of the operands is true. So if we say it's raining or it's sunny, then this will be true if it's raining. It will be true if it's sunny. It will also be true if it's raining and sunny, which is a bit uncommon in many parts of the world, but it's not impossible. On the other hand, if it's not raining and it's also not sunny, then the statement is it raining or is it sunny will be false. Not swaps the values around. So not of true is false, not of false is true. If we run this program, we will get false, true, and false. There you go. So the first false is because I is true, but j is false, so true and false is false. I or j, true or false, is true, but not I, not true, is false. There you go. You can get a Boolean by comparing values of other types. So let's suppose that I and j were, again, 2 and 3, like in the previous examples. If I were to state I greater than 3, then I will get false, because, well, 2 is not greater than 3. I greater equal than 3, that would also happen to be false. If I were to say I greater equal than j, I times 2 greater equal than j, now finally we get true. There are various operators, and these operators have a precedence, and this precedence makes it possible to write bigger logical expressions. This would be a logic expression without having to put too many brackets. If you have doubts, well, you may always put the brackets, but if you know the precedence of operators, this might save you from having to type some extra brackets. A few brackets might make code more readable, because, I mean, you shouldn't expect everyone in your team of developers to know the most exotic operator precedence rules, but having brackets everywhere is also going to look ugly. Now, in this case, the precedence of the multiplication operator between numbers is higher than the precedence of the comparison operator, and the comparison operator has more precedence, has a higher precedence than AND, so that we can write an expression like this, with a combination of arithmetic operations, which take the highest precedence, in order to be able to compare the results of arithmetic operations, and then a logic operator that combines the results of multiple comparison operators. So logic operator has the lowest precedence in order to be able to perform comparisons between arithmetic operators. So it's actually pretty well thought through this. One might wonder though, okay, that's all nice, and we all know from school that multiplication and division have higher precedence than sum and subtraction, etc. But how about these operators? What kind of precedence do they have? Does AND trump or not? Well, interestingly enough, so if you consider true to be the same as false, true to be sort of akin to 1 and false to be akin to 0, then you might realize that, yeah, because true and true is equal to true, but true and false is equal to false and true, which is equal to false, well, you might realize that, oh, and of course false and false will be still false. Well, this means that true and false are behaving like 1 and 0, and AND is behaving like multiplication. Okay, that's interesting. Now, on the other hand, when dealing with OR, true or true is true, true or false is true, false or true True or false is true. Oh, okay, I screwed up one of these equalities. Okay, very good. False or true is also true, and finally, false or false is false. Okay, so if you especially focus on the last ones, well, if you consider or to be plus, then 1 plus 0 is going to be 1, 0 plus 1 is going to be 1, 0 plus 0 is going to be false. And in this case, 1 plus 1 is going to be, well, not 2, but again 1, because you could imagine that this is a plus operation that caps our values at 1 instead of going beyond. It still works. Okay, and not, well, okay, so not true is false, and not false is true. So you could consider not to be a sort of 1 minus x. So not x, you could consider it to be a sort of 1 minus x operation. So this means that not will have the highest precedence, or will have the lowest, because sum has a lower precedence than multiplication, and multiplication will have a higher precedence than or, than plus, but it will have a lower precedence than the negation. Pardon, a higher precedence than the negation. Apologies, because the negation is a subtraction. Okay, so that's kind of a funny way of remembering operator precedence. Just translate it to numeric algebra, and the precedence will be according to regular algebraic rules. Another type that belongs to the primitive types, so to the simplest types that the language supports out of the box, are strings. Strings are pieces of text. Let me declare two variables of type string. Now, variables of type string, well, they support a less rich algebra of mathematical operators like the numeric types, because strings are not really fully comparable to numbers, but still we can add strings together, resulting in the concatenation of the strings, so the strings are just put next to each other. We can also add constant strings in the mix, no problem. Now it looks a bit more readable. We can also compose strings together by making use of the interpolation operator. Now the interpolation operator is super useful, and it leads to complex string concatenations that are faster to compute, because string interpolation is better optimized than just adding strings together. Adding strings together creates a lot of intermediate strings that string interpolation doesn't, and also the code looks, even though this is subjective, the code looks a bit better. Now, string interpolation is based on backticks instead of the double or single quotes that characterize normal strings. So double and single quotes are essentially the same, they behave the same way, but backticks, on the other hand, they are special because they allow for string interpolation. Then, dollar and curly brackets with an expression, an arbitrary expression between the curly brackets, will take the value of the expression and turn it into a string at this place. Then you can have whatever characters you want. In this case I'm putting a space, but I could also put, I don't know, some underscores, for example, then another expression, and the string that results, let's take a look, is hello, the underscores world. So interpolation refers to the fact that you have a sort of string template, and you interpolate this template along the different values of the variables within this dollar curly bracket component of the string, variable component of the string. Strings support many operators, I should say operations, such as calculating the length in characters. 5, hello has 5 characters. But also, well, let me show you how we could generate a string where the number of exclamation marks comes from a separate variable. I will just call this variable n, the count of exclamation marks. At some point the name we give to variables is very important, but not yet, not at this level of software writing. Now, if I were to put the exclamation mark here inside the dollar curly bracket block, then I can calculate something. And what shall I calculate? Well, I shall calculate the repetition of the exclamation mark n times, where n is a variable of number type. Now we get hello world and 5 exclamation marks, but it's quite easy to adjust the number of exclamation marks because it is parameterized with variable n. Finally, among the many operators that we have here, I will show how to replace the lower case letter h with a capitalized H. So we finally get hello world with a capital letter H. There are many more operators in the string library. So if you look at any string and you press the dot, you will see plenty of different things we can do. Just play a little bit with them, and well, for the rest, search engines are always available. The basic types, the basic primitive types, support not only operators, but they also support restrictions in the type system of TypeScript. What does this mean? It means that if we have variables of types that cannot be mixed together, like we have our hello variable and our n variable, if I were to attempt to perform some nonsensical operation, just I divided by n, I would get an error. The error is stating, and if you look at the console, the error is written, that the left-hand side of an arithmetic operation must be of type any, number, big int, or an enum type. So basically, well, any we're going to ignore for the moment, but what we're being told is that in order to be able to divide something on the left-hand side of the division, there must be something that is a number. And this makes sense, because how would we divide a string by 3? A string is a piece of text, and it doesn't make sense to state, okay, we divide a piece of text by 3. Come on. Now, mind you, in JavaScript, we wouldn't have gotten any error. Even more interestingly, TypeScript is attempting to just translate our nonsensical little program into JavaScript in order to give us the possibility to run it in case we really wanted to. And what you see is that, okay, JavaScript is sort of stumbling through this typing fiasco that we just typed, despite TypeScript's advice not to run the program. And what we get by dividing a string by a number is none. None is a special value that signifies not a number. Not a number is a very nasty thing because it's sort of contagious. Whenever you try to take a not a number and do something with it, like add it, multiply it, etc., the result is always not a number. So not a numbers tend to propagate like, yeah, really, they are a sort of sickness of numbers that is unfortunately not really curable and will lead your program to crash and burn with great likelihood. So it is best to heed to the compiler's warnings, because those warnings, this is an error, not a warning. It's best to listen to the compiler's errors. If the compiler says there's an error, do not run your program, fix the error. And in case you wanted to make sure that TypeScript doesn't generate files when there's an error, you can use no emit on error, which will not create a JavaScript file or which will not output the result of compilation to a JavaScript file if there is a compiler error, which is actually quite a good behavior, better than the default. Okay, very good. Now, one note that I want to share with you is that the type checker is a little bit pessimistic. Now, in general, if the type checker signals an error, there will very likely be a manifestation of this error when you actually run the program. But there are cases when the compiler is not sophisticated enough to see that a program that on the surface has a type error would still run safely. So the compiler excludes many programs by signaling an error that would actually crash at runtime or behave very badly at runtime, but it will very occasionally signal an error in a program that would otherwise be able to run fine. I'm saying this for completeness because in general, let's say that you're working in a team and there's a junior developer who says, oh, stupid TypeScript compiler, it's making me waste so much time by fixing all these errors. Oh, I know what I'm doing. No, in general, that's not true. The compiler is in general very right. But there are cases, rare but not impossible, where the compiler might not be able to understand all of the complicated logic. So, okay, that's it. I've said it for full transparency. You might have also noticed that type checking is doing its very pretty and pleasant job, even though we have not put any type annotations. So in JavaScript, in Java or C# we would have to state that I is an integer by, for example, saying, well, this is not valid TypeScript, but still, int I or something like this. Int, or in our cases it would be string I. Now, TypeScript makes use of so-called type inference. Type inference is a simple intelligence, a simple mechanism that guesses the type of our variables and constants by looking at what's on the right-hand side of the first assignment during the declaration. So without any effort for the developer, TypeScript has guessed I is a string and n is a number. This reduces verbosity. That's quite nice, actually. So, the types that are inferred are fixed. Even if I is a variable, I cannot just reassign it to a number. We will get an error. Let's remove the error on line 5. Now we see that there's still a residual error in our program that says type number, that refers to the value 2, is not assignable to type string, that refers to the inferred type string of variable I. We can give hints to the, well, mandatory hints to the TypeScript type checker by writing a colon after the name of the name that for which we want to specify a type, and then specify the type we want. So in this case, I could say I is a string and its value is hello. If on the other hand I want to say I is a number and its value is hello, now I get a compiler error, but the compiler error is higher up. Now, interestingly, if we restore our error here on line 4 that says, okay, you're trying to divide a string by number, now this makes perfect sense because TypeScript is making the reasonable assumption that on line 1 I intend I to be a string because I'm assigning value hello. But if I really meant I to be a number by providing the type hint or the type annotation, well, now the error has moved from line 4 to line 1 because the problem here is that I'm trying to assign hello, which is a string, to a variable which has now been declared as being of type number. And line 4 simply works because, yeah, now I'm dividing a number by a number, and that is perfectly safe. So this is the basis of type checking. As part of our discussion on the basic constructs of TypeScript as a programming language, we now dive into conditionals. Conditionals are, in a sense, the foundation of intelligence of our programs. Why is that? Because conditionals make it possible to take a program which, in its simplest form, would simply be a sequence of statements performed one after the other. And with only that kind of statements, we don't really have much more than just a very advanced pocket calculator. And thanks to conditionals, we can introduce some logic that allows us to perform one instruction rather than the next based on some dynamic criteria of selection. The core of conditionals is the if-then-else statement, but there are two more conditional structures that we will look at, the ternary operator and the switch case, which have slightly different real-world scenarios, but eventually all boil down to the same process. Now, suppose that you have some variables, let's say I and j. Now, in this example, I and j both have a value that we know already, because, well, I is 2 and j is 3. But in real life, these variables might come from user input, they might come from an API call, they might come from wherever. We might simulate this kind of uncertainty by, for example, getting random numbers. Well, actually, you know what? Let's do it. Math.random gives us a random number between 0 and 1. And now we will, let's call this the random seed. Then we have two values, I and j. Okay, very good. And then depending on the random seed, we are going to print the sum of I and j or the product of I and j. So we are going to use the if statement. Within the brackets of the if statement, we can put a conditional expression. So for example, I could say that if the random seed is greater than 0.5, and then between curly brackets, I put the instructions that we want to perform in case the condition between the brackets evaluates to true. So I can print I plus j in this case. Actually, you know what? Let's put a little bit of attention in this. I, then we also tell the user what is happening. I plus j equals, and then I plus j. Okay, very pretty. We can also put optionally the else block between curly brackets again. The things that the statements that are after the else that are contained in the else block will only be executed, will only be performed if the condition between brackets right after the if evaluates to true. And in this case, we will multiply I and j. Okay, very cute. Now let's run this little program, and we get that 2 times 3 is 6. 2 plus 3 is 5, and well, we've kind of exhausted the possibilities. Not very exciting. It is possible, of course, to do all sorts of things when it comes to conditionals. For example, we might say, okay, the result is I plus j, and here we could put the result. Now, notice what happens. In here, line 12, after the conditional, I have variable I. Well, let me trivially show. I have variable I. I also have variable j. I also obviously have variable random seed because, well, these are all the variables that we've defined. But what if I try to print a result? Look, there is no result variable. Even if I try to print this, I get an error that says cannot find name result, because a result is a name that is not bound to any value. But why is that if I apparently declare the result on line 6? Remember that we discussed that anything between curly brackets or curly brackets in the language define a scope, and the variables defined within that scope stick to that scope. It means that the closed curly bracket here on line 8 is the place at which result declared on line 6 stops being available. This also means that result is not available in the else block, because result only exists between the curly brackets within the block delineated by the curly brackets between lines 5 and 8. We could define another result variable, but mind you, it is not the same on line 9. And even though we have two variables, result, both of type number, declared in our branches of the if, both of these variables have a very precisely delineated scope, which is the first one, the one declared on line 6, only exists between lines 6, 7, and 8, and the one declared on line 9 only exists between lines 9, 10, and 11. Both result variables cease existing at the end of their respective block, meaning that on line 16, even though here one might argue, but wait a second, both branches of the if contain the result variable. Yes, and still, both those result variables have been cleaned up at the end of the respective branches, and so it does not exist anymore. Okay, this also means that we can tidy up our code pretty neatly, because yeah, we can declare temporary variables that are only relevant within one branch of the if or the other branch of the if. They are usually called the then branch and the else branch. And then these variables do not pollute the logic of the rest of the program, because yeah, they are simply cleaned up. It is also possible to nest. It's also possible to nest conditionals. So, for example, one might say, okay, we have the random seed, but we want to perform the same operation twice. So, in the then branch, so in this case, we want to perform another check. So I'm going to say if math.random is greater than 0.5 again. So again, with a 50% probability, I perform a sum, and otherwise, with 50% probability within this branch, so a global probability of 25%, I perform a subtraction. And then I'm going to replicate this structure here for the product and the division. And now I have achieved 4 branches. Notice therefore that by branching within branches, oh, let me remove these very ugly prints at the end. Yes. And we have 4 possible outcomes, each and every one with a different probability. Eventually we're going to hit the division, right? Yes, there we go. And now we touched upon all branches. We might also do something like this. We might also redefine the same variable, and I find this quite interesting because now, yeah, we have another nested random seed. This is not necessarily a good practice, because it can lead to accidental mistakes. So I'm not saying it's possible, but be aware, this is how the language works. The language does not make this, does not disallow this. So yeah, you might be advised that this is something that might happen. Okay, and you can see we've already hit the second branch. So so in order to get to line 11, we had to have a true on this condition and a false on this one, showing that the random seeds are indeed 2 different variables. This doesn't necessarily simplify the flow, the logic flow of the program. So again, I would only use this technique, which is called the shadowing of variables, because this random seed hides this other random seed variable, and we say, yeah, they're shadowing. So the 2 variables put each other, or the second variable puts the other in the shadow. Yeah. We can do all sorts of patterns of combination of conditionals. So in this case we have nested conditionals, so we can put conditionals one inside each other. You can see that this conditional here is clearly nested inside the conditional on line 5, and we can also cascade conditionals. So in this case, what we could have done, we could have also said, okay, you know what, we partition the random seed because it's a random value, so we can go both ways. If this is smaller than 0.25, okay, we go for the first option, and then we can combine, we can cascade, and in the else we have another if immediately. This is okay, if the random seed is smaller than 0.5, then so the sum is the first 25%, then between 25 and 50%, of the range of the random seed, we have subtraction. And of course, is if the random seed is smaller than 0.75, then we can perform the multiplication, and in all other cases, so between 75 and 100% of the range, we perform subtraction. And it's interesting also to reason about this because, look, so if we are in the else, then here we know that the random seed, well, that this condition is false, because otherwise we would have jumped into line 6 and not to line 9. So here we know that the random seed is greater or equal than 0.25. So here, implicitly, we know that the random seed is between 0.25 and 0.5. One might remove the else. I would definitely not advocate doing this, and writing it like this. But, well, now we are performing a series of checks which are quite redundant, because, well, we're not really taking advantage of the power of the available else branches. So yeah, I really wouldn't do it like this, but yeah, the three versions of programs we have seen are semantically equivalent. Something I would definitely advise against, though. So this is kind of iffy already, it's kind of ugly, but I think the worst could be mixing different styles of nesting. So if one said, now this I'm just going to show the shape of this. You could have the first if, then the three else ifs that we just saw. But inside the first if, you could have the second if. So at least there has to be some consistency when there are different cases. So if the cases are all equally, if the decision is at the same level, it makes sense to use this cascading structure that I have. If the decision really depends on knowing the outcome of the previous decision, then the nesting is better than the cascading. And here, I think it's worth it also to spend like a few seconds blabbering about this. This kind of micro decisions on how to structure code, they are very important because they decide how do we perceive the sequence in which the computations are happening. And it's this aspect of making lots and lots of micro decisions that requires a deep understanding of the problem you're trying to solve and a deeper understanding of how to model knowledge about the solution to the problem, because code is a solution to the problem. And this is where the art and craft of programming stops being an engineering discipline and really becomes an artistic discipline in a sense. And sometimes people say, okay, how do I know, especially when they're beginners, of course, how do I know how to write the first program? And really, yeah, it's really not easy. It's like a writer saying, how do I write a good book? Yeah, crap. It's a question without a good answer. It really has to do with the structure of the domain you're thinking about. And the sucky answer is it needs a lot of trial and error and repetition to discover your own style. And lots and lots and lots of mistakes. Okay, but first, we need to really understand how the language works. Notice that I've used the two words, expressions and statements. And I use them precisely, but I would like you guys also to know what do they really mean. So an expression is something like this: random seed is smaller than 0.25, or I plus j, or also this whole string here is an expression. So an expression is a piece of code that contains a series of operations that need to be performed. It reads variables, an expression, it reads names, variables or constants, and assembles a result that can be further used. But an expression doesn't really change the state of the program. It does not modify the value of a variable. It does not introduce new variables. On the other hand, something like let the result is I plus j, this is a statement. Statements can and often do change the state of a program. And this is a statement because, well, it creates a new variable. Also console.log blah 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 on line 7, this here is also a statement. Why is it a statement? Yeah, because it changes the memory of the application. Namely, it changes the memory of the terminal by adding a line, a printed line, to the terminal. Also, an if then else is also a statement. Even if it doesn't necessarily contain statements in the then and else block, there is an invisible variable, which is the so-called program counter, which points at the instruction that's currently being executed, the statement, the current statement, a sort of arrow that says this is the current statement. And well, the if then else changes the value of the program counter based on the condition that is right next to the little keyword if. And this program counter is very important because which statement you are currently executing is quite a big deal to modify that. And that is a variable which value implicitly changes with if, and this makes the if statement a statement and not just an expression. So to recap, expressions do not perform operations that are immutable with respect to the state of the program, and statements can and usually will change the state of the program. There exists a conditional expression. The conditional expression is a sort of micro if then else that only affects expressions. So it's not a conditional statement. Let me show how this would work. So let's say you might have noticed that all of these branches eventually end up in us defining a result. So for now, let's forget about the different console.logs. I will just move them out of the way because, well, we still have to think about it. We're not really going to butcher our program, but for now, if we were to replace this this little program with something that simply computes a different result every time and prints it, then, well, one might simply wonder, okay, but why can't we simplify this program by having the console.log result the same at the end, and then defining the result in a way that is conditional to the value of the random seed. Now, let me show you how this is done. What we can do is we can do the following. We can take the condition and say that the result, now, when the random seed is smaller than 0.25, then the question mark becomes basically the limiter. Then we go to I plus j. Colon is the same as else, literally the same as else. So else, when the random seed is smaller than 0.5, but mind you, we also know that it's greater or equal than 0.25, then I can pick this. When the random seed, I will just methodically simply pick, yes, the pieces of our program as it was before. Then you can clearly see we're not really inventing anything, we're just restructuring the application. And then, just because I have been writing software for so long that yeah, it has screwed up probably some of my cognitive abilities, so now I have to have aligned code. Okay, very good. Now, in the last else, indeed, we pick I divided by j. Okay. The slightly unfortunate side effect of this program is that, yes, it computes the result. You can also see it's shorter. This is a more functional programming style, and functional programming does tend to be more concise, shorter, more packed, densely packed with information. But also, what just happened is that we've lost the full print of the string. Okay, now, in an effort to be slightly more elegant, let me do two things, because if you notice, all these strings are basically the same, but the operand is different, and the operand is just a string. So what we can do is the following. We can assign two variables at the same time. I will use the tuple syntax. We will dive into tuples later, but for now a tuple is simply multiple variables that we carry together between square brackets. So result and, oh sorry, not operand, operator, okay, and this has to be assigned in all cases. So the result will be the same arithmetic expression, and just the operator we've applied will be a little string next to it. And there you go. Now TypeScript is smart enough to have guessed that the operator is a string and the result is a number. Very impressive. Now we can take this sort of template for strings, and lo and behold, instead of just putting a plus here, we will just take the operator from wherever we picked it, and now what we're doing is we're assigning multiple variables, the result and the operator, on each of the sort of branches, if you will, of this sort of if then else. When the declaration is long enough, like this between square brackets result operator, it might also make sense to start on a new line in order to make the code breathe a little bit. So now we can see that the program, four different steps in one go. That's very lucky. That doesn't happen that often. Okay, so the conditionals we've seen so far make it possible for our program to adjust its response to a situation that it detects. In the case of our very simple example that we have on the screen, the value of the random seed defines this situation between air quotes. So if the random seed is smaller than 0.25, then we produce a given response. And if the random seed is between 0.25 and 0.5, we produce another response, and so on. You can imagine that the conditions we check might have to do with all sorts of things: user preferences, external sensors, all sorts of things that require an adjustment in the response of our program. And this is very important in order to make our programs more flexible and more dynamic and more capable of adjusting to you could even say stimuli, and if those stimuli come from API calls, user interaction, timing, etc., well, then this is really the basic building block of some degree of intelligence. Next to conditionals, we have loops. Loops make it possible to shrink or expand the number of instructions of our program. The simplest sort of conditional that we're going to study is the the simplest form of loop that we're going to study is the while loop. While loops look like this. We have a condition or conditional expression, which is here between brackets, very much like for an if then else. Then we have curly brackets, and here we have the body of the while loop. So how does a while loop really work? First, it evaluates the conditional expression. If the conditional expression evaluates to true, it runs all the instructions in the body. And then it goes back to the beginning. It starts again evaluating the conditional expression. If the conditional expression evaluates to false, it skips to the first instruction after the while loop. So it jumps out of the while loop as soon as the conditional expression is false. Mind you though, this is not really a concurrent process, the evaluation of the body and the evaluation of the conditional expression, meaning that the while loop will terminate running each instruction of the body before re-evaluating the conditional expression. I have seen beginner practitioners implicitly expect that as soon as the conditional expression is made false, the body will be interrupted even halfway. No. So evaluate the conditional expression, run the body in full if the conditional expression evaluates to true, and then go back to the conditional expression and repeat the while once again. Let's see a very simple example. Let's say we have a counter, starts at 0. Let's say we have a target, that has a value of 10. Now, then we could say, while the counter is smaller than the target, okay, so what we want to do is we want to keep running the body until the counter has reached or exceeded the target. Then I could say, okay, just print an informative little string saying the counter has value counter, and we still have, and then target minus counter to go in order to reach the target of target. A lot of verbosity for a very simple task. Now, of course, if we were to run this program as it is now, well, the condition is true and remains true forever because we're not really changing the counter or the target. In order to ensure that a while loop does not run forever, we must get closer after every iteration of the body to getting the condition true. This is an interesting concept. So imagine that indeed in our case the condition counter smaller than target, well, at any given time it's either true or false. But there are different ways for this condition to be true. So if the counter is 0 and the target is 1,000,000, yeah, obviously 0 is smaller than 1,000,000, but the condition is, you could almost say, very, very true. On the other hand, if the counter is 999 and the target is 1,000, yeah, it's still true because 999 is smaller than the target, than 1,000, but they are very close and the condition is about to be flipped. So whenever you formulate such a condition, you should realize that there is an implicit distance in number of steps, iterations, whatever, between the condition being true now and being false eventually, and you have to take steps that bring you to the condition to be false in order to make sure that your while loop is going to terminate at some point. So in our case, we could say, okay, then the counter becomes counter plus 1. Or if you want to use the C++, C++, all the style syntax, yeah, you can simply write counter plus plus. To be honest, I don't like it anymore. I'm getting old. Or you could say, no, we don't increase the counter, we decrease the target. Or both. Why not? Depending on your application. What we shouldn't do is move both at the same speed. But if one moves faster than the other, for example, yeah, it is a moving target, but the counter takes bigger strides than the steps of the target. So there you go, and yeah, kind of funny because in the beginning we say the counter has value 0 and we still have 10 to go in order to reach the target of 10, but then the target is moving 11, 12, 13, but the counter is growing even faster. Now, so the basic, well, but actually let's go to the cleaner variant where we simply increase the counter by 1. And let's see this in action. Okay, so the counter has value 0, and we still have 10 to go in order to reach the target of 10. Counter has value 1, counter has value 2, and so on. And you can see that I'm also plotting the still have so many to go, which is the distance between the condition being true now, but becoming false eventually. Loops, just like conditionals, may be nested as much as we want. Let me show you an example. I do love building little two-dimensional figures as examples of loops and conditionals and their nesting. So let's say we want to build a figure, and this figure is supposed to be a square of asterisks. Not the most exciting scenario, I know, but still a very good illustration of how to compose loops together. So the size of the figure will be 5. Let's begin by, we build up the rows, and the rows have a different vertical coordinate, so we start at y. While y is smaller than the size, well, y will be incremented because here we're supposed to build row y. And then we do the same. No, I'm not going to copy because I will be a good Boy Scout. We now fill up all the columns. We fill up all the columns of row y. So x is 0, while x is also smaller than size, x is x plus 1, and here we have to build row y, column x. Now, easier done than said almost, because we add to the figure just a single asterisk. Now here, between lines 13 and 15, the row is finished. So the y is complete. So we add a /n, which is a special character that sends our string to a new line. Let's print this. Let's print the figure, and with a little bit of luck, there you go. There's our lovely little square. We might play around with this concept. We might say, okay, but we want to have alternating rows of asterisks and spaces in between. So we could, for example, want to make, or we could make the square empty. Let's do this. Now, in order to make the square empty, whenever x is greater than 0 and smaller than size minus 1, and the same for y, we put a space instead of an asterisk. But you know what? Let's begin with a simpler, let's do this step by step. So if x is equal to 0, so the first row, the figure gets an asterisk added, otherwise we put a space. And there you go. So we're only putting the values for which x is 0 in this sort of imaginary grid to an asterisk, the rest is a space. Alright, now we know that x is 0 is an interesting condition. Let's park it. Then if y is 0, there you go, that's the first row. Okay, that's also another interesting condition. Let's just gather all of them. If x is size minus 1, because that is the last iteration, and then we get the last column, very good, and because we're dealing with a square, also y is equal to size minus 1 will be the last row. Okay, very good. Now we can combine them. So when do we want to have an asterisk? Well, either for the first row or for the first column, first column, that's x0, first row, that's y0, last column, that's x is equal to size minus 1, last row, y equal to size minus 1. And there we go. Our little square is now hollow. It's a hollow square. Okay, very cute. We can keep playing with this. We can have checkerboards. We can build triangles. We can do whatever we want. Let me show just the triangle. So, for example, if we say x smaller or equal to y, then we get a triangle. If we say x smaller or equal than size minus 1 minus y, then we're flipping the y-axis around, and so on. We can play with this as much as we want. We can build all the sorts of triangles that we might want. I mean, yeah, I just leave it up to you. And you can see already that the combination of while loops and if conditionals is quite powerful. We can achieve many complicated figures, and these figures are a reflection of the fact that, well, we can build structures that are like when composing two loops together, then we're dealing with a multi-dimensional little space. In our case, a while loop inside a while loop with this specific structure means basically, yeah, a sort of grid of computation. The conditional makes it possible to do things. Well, in the inner while loop, we're going to do things to the cells of this grid. I like to visualize things, it really helps me. And if we add another while loop on the outside, so if we added another loop while z smaller than size, you can imagine that this would amount to building a sort of a three-dimensional cube of computation, and so on. We can go on as far as we want, obviously. There is no limit to this. We can also do things that are not squares, cubes, or lines, or hypercubes, but that requires different patterns that transcend loops even, that can be achieved with some forms of recursion. But we will see that in the next lesson. And depending on where we put the conditional, indeed, we're acting on the full rows. If we were to put an if here, then we would influence the definition of the whole row. If we put the conditional here deeply nested in the innermost loop, then we're modifying the way the single cells are being processed, and so on. And this really gives a lot of power, because you could also have multiple loops nested inside each other with multiple conditionals nested inside each other, etc. Once again, it's this sort of freedom and unconstrained ability to express your translation of a domain into code that is the beauty and the challenge of programming as a discipline. TypeScript also knows another sort of loop, which is the do-while. Do-while loops are, let me just cut the while definition. They are essentially the same with one not so minor difference. The evaluation of the condition will happen after the execution of the body. So this specific program is effectively the very same as the while that we had before, but the do while assumes the do while runs the body first before evaluating the condition, and this is okay whenever you know that your code will need to run, the code in the body will need to run at least once. Do whiles are not really used very much in practice, but still, you know, well, they exist, and yeah, sometimes you will encounter them in practice, so might as well know how they work. One of the challenges, though, of while loops in particular, while do and do while, so both flavors of while loops that we have just seen, is that it's relatively easy to write a while loop that by accident does not terminate because you just forget to perform an increment, like in this case. And eventually the program will run out of memory or encounter some nasty situation from which it can't recover, and then the whole program, well, it terminates because of a catastrophic failure. And this is not exactly the kind of power that you really want to wield accidentally, you know. This sort of thing can happen. It's too easy for it to happen. In order to limit the destructive potential of these very open while loops, without introducing hellish constructs such as break or continue, and no, I'm not going to show how break and continue work, because I do consider them to be way, way, way too dangerous to be used in practice. Like, they introduce a complexity in predicting how a loop is going to behave that I wouldn't wish on my worst enemy. So let's keep things simpler and cleaner, not more complicated with constructs from decades ago. So in order to manage the complexity of these open-ended loops where we define the step and the target, etc., computer scientists many years ago introduced another kind of loop, the for loop. The for loop actually contains a series of loops, just like while, do, and do while, that are built to perform a number of steps precisely limited. So in our case, we know that we want to go through all the rows, and we will start at row 0, and we will stop when we reach row size -1, and we will increment the row counter by 1. So this, the line 5, line 20, and line 21 is such a common pattern that the for loop makes it possible to express this iteration pattern according to a fixed template that is easier to write and easier to read and harder to get wrong. Let me show you exactly what I mean. So even the declaration of the variable happens inside the for loop declaration itself. We don't need this while here, because the condition is the second component of the header of the for loop, and the increment is the last component. It's quite common for loops to simply write y++ or ++y. Very same applies to the for loop that deals with the increment of the column. Notice that I'm also losing lines of code we're losing lines of code because for loops gather together on the same line, the line of the header of the loop itself, everything that is relevant to understand which steps is the for loop going to take. And now, there you go. The program behaves exactly the same. There is also one very interesting side effect of using a for loop as we have now, rather than the while loop we had, that here the variable, the iteration variable I, is only available inside the loop and does not end up accidentally existing outside of the loop, outside of the whole loop. So if I were to try to print y, in the previous version, y still existed because it was declared before the loop. And that's kind of undesirable because if you think about it, we don't really want the iteration variable that is needed to keep track of which step have we reached in our loop to have this variable for whatever reason keep existing forever after the loop is done. So the for loop also forces us to keep things clean and self-contained. So neither y nor x here exist. They are cleaned up. So the for loop introduces a series of very useful concepts that are neatly bound cleanly together. The idea that you declare some variables that are only required in the loop itself, in our case x and y. The fact that you go on until a given step and that at every step you perform some increment or decrement or whatever on the variables that you just introduced. For loops are so powerful and so common that they are also available in the shape of for-off loops when dealing with collections and arrays. I will give you a quick introduction now, but then we will talk about arrays and things that can be iterated more in subsequent classes. Let's say that we have a series of people, John, Jane, Jim, and Jack. Let's call them the G-pol because they all start with a J. Now we can say that we have a for of, and then look, this is actually pretty clean. You say here, for example, Jerson of G-pol, and what's going to happen now? This of syntax means that we're going to go through all the values, all the items inside the array G-pol, and each one of these values will be assigned in turn to the variable, or in our case to the constant Jerson. Now it's funny that I want to call it a variable because it varies with respect to the different iterations of the for loop. So that is kind of a funny distinction. Now let's print each value of Jerson. As you understood, Jerson is person with a J. Oh my god, that's terrible. And you can see John, Jane, Jim, and Jack. For of loops are particularly useful when dealing with a collection where we don't really care about tracking the position in the collection we're currently iterating. So, when we just want to say, take one step at a time by moving on to the next element of an array or a list or anything else that we can perform an iteration over, we might not care about the fact that, okay, this is step 0, step 1, step 2, step 3. We simply want to know, okay, just give me the element, I just want to print them all. I don't care about this being element 0, 1, etc. And that's where the for of comes in extremely handy. In other languages, such as, for example, C#, the for of construct has a different name and even a different syntax. It's called the for each. In some other languages, where for each is quite prominent, have sort of set the tone that maybe this should be called for each instead of for of. This for of syntax does smell a lot of JavaScript specificity. This is not necessarily a wrong thing. I'm just saying that you might find in some JavaScript libraries a mention of for each instead of for of. I think even in the array itself. Yeah, where it's called for each instead of for of. So there is some minor inconsistency, but it really doesn't matter. The semantic model of for each and for of is 100% overlapping. It's 100% the same. So, you know, that's good news. Well, now, even though this is quite clean, you might also want to be very careful because there is also another JavaScript specific loop, which is something that iterates the keys of an object. And yeah, this is mostly done to perform sort of dynamic runtime inspections of all the attributes available on a given object. And it's easy to confuse them. For some people, using in for iteration is even more natural for iterating the elements as using of as a syntactic particle. I know that this tends to confuse the hell out of me personally. Be aware there are two different things. The one that in most cases you will want to use is for each or for of, and not for in. For in is quite an exotic construct, quite an exotic edge case for advanced library manipulation. Just so you know, a word to the wise, let's say. This desire to simplify and structure loops doesn't stop at for of. We will see that most advanced practitioners in practice will even rarely use loops and more often use higher order functions in order to manipulate collections with map, filter, reduce, etc. So looping statements such as while are very open in nature, and they do offer us the freedom to write loops in any way we might want. And when you need to perform a complex computation, let's say if you're building a machine learning algorithm and you need to perform a loop until some error measure gets smaller than something or apply something like the elbow method, then a while loop is going to be your best friend. Then it makes a lot of sense. That's why modern languages like TypeScript still feature while loops and do while loops as well. For loops, on the other hand, were an early attempt to simplify iteration patterns on top of collections, but higher order functions like for each that we just saw, map, filter, etc. have brought us even further in our ability to capture these iteration patterns in such a way that greatly improves readability, reduces the amount of code, and reduces the margin for errors. So we will dive deep into those, but for now be aware of the fact that we have many ways of looping, they are powerful, but there is plenty more to expand our knowledge on how to process different things, process the repetition of logic according to a dynamic pattern of shrinking or expanding of our programs. Having said this, we can consider the basic introduction to TypeScript concluded. I hope it has been interesting. I'm always open for feedback should you want to leave any sort of feedback. I would like to thank you very much for listening. Thank you very much for participating in all of this. And I hope that in its own way, this course can contribute to your own personal growth and to getting you closer to the goal of learning the beautiful craft, art, and science of programming. Thank you again very much, and until next time.